Hello, everybody. Welcome back to Calculus. Today is the lesson over section 5.5. It begins applications of integration to the sciences. Now, the first section, 5.5, is pretty straightforward because we've been practicing to death already. It's basically about projectile motion and the relationship between position, velocity, and acceleration. So we'll get into that one more time. You have some more problems to deal with involving that, and it won't be that bad of an assignment. I do warn you, the section coming up after this, 5.6, is specifically about some applications to physics and engineering. Those are a little more tricky. So if you haven't taken physics, listen to lessons very carefully because I'm going to explain the physics concepts behind it and the calculus. And if you're stuck on that, and I'm not around, there are people that consult. You got Carson, Cass, both of them are in calculus, both of them are in physics, so they'd be a great resource because they already know a lot of the theory behind it. But we'll get to that section next. Right now, projectile motion problems. But before we do that, let's do our warm-up real quick. The warm-up is kind of involving a little bit of this stuff. Can we get used to it to remember any of these concepts about projectile motion? So number one, write the equations for velocity and acceleration in differential form. Number two, I'm telling you some initial conditions. If the velocity at time 0 is 20 meters a second, and the acceleration at any given point in time is -10 meters per second squared, determine your velocity at time 3 seconds, okay? And the last one, number 3, is a physics problem, okay? But it's got some calc built in it. It says, and you're not supposed to understand it right now. If you do, fantastic. If you don't worry. We'll talk about that in the next section. But it says, using the definition of work, which if you're not in physics, you'll know, and the fact that F is -g m1 m2 over r squared. Might not know that equation if you're not in physics. If you do, I'm sure you recognize it. Find the change in potential energy between the Earth, okay, so you got this big ball of Earth, and this 1 kilogram mass that's lifted 1,000 meters off the ground. How much energy potential does it gain in that case? And there's some constants down below to help out with that. Let's do one at a time. So number one, write the equations for velocity and acceleration in differential form. Well, that's pretty straightforward, okay? All that means is, what is velocity? It's the derivative of position with respect to time, okay? So I have the classic figures I have where I have x, v, and a. If you start with an x and take a derivative with respect to time, you get down to velocity. If you have a velocity and take a derivative with respect to time, you get down to acceleration. And this section that we're talking about today will specifically probably be going the other way. They're saying, here's your equation for acceleration. You're going to integrate it and get back to an equation for velocity, which you'll probably integrate also to get back to a position of, equation for position. So you should have an equation for position, velocity, and acceleration. There's initial conditions you'll plug in, and that's kind of what we'll be doing, which is what number 2 basically is. So number 2 says, your acceleration at a certain time is -10 meters per second squared. Well, what is acceleration? It's dv over dt. It's how quickly your velocity changes with time. So dv over dt is -10, okay? Now, how do you go up a level? You got to integrate, but this is not set up to integrate. So you multiply both sides by dt. You get this little differential equation that a little change in volume, a little change in velocity, dv, is equal to -10 times a little bit of change in time, dt. Once you got that set up, just like the last sections, once you got your differential little equation kind of set up, d something equals d something else, all you got to do is slap some integrals on this. So slap an integral on it. And here's one thing I do want to kind of concentrate on, okay? What should the limits be? You don't need an arbitrary constant when you have definite integrals. You don't need a plus c. You could just integrate these separately, put a plus c in there, and figure out what the c is based on the initial conditions. But going up a little higher, let's talk about how you just do it with definite integrals. So on the right, since you're integrating with respect to time, you're trying to figure out how this changes from your starting moment, time is 0, up to some arbitrary time we'll call t, okay? If you integrated the right-hand side, which was with respect to t, had dt stuff, okay, from 0 to t, then on the right side, when you integrate it, your limit should also represent what you're integrating at time 0 and at time t. Well, the left-hand side is the integral of dv. That's in terms of velocities. So your limits would be at the bottom, the velocity at time 0. At the top, your limit would be the velocity at time t. They're both representing the same thing on both sides. time goes from 0 to t. But over on the left-hand side, it's, well, yeah, I guess I'll teach you backwards. Over on the left-hand side, you're integrating v. Well, then the limits would represent the velocity at time 0 and the velocity at time t. Your integration with respect to t, well, you're just going from 0 to t, something like that. When you do that, when you integrate dv, you just get v. And if you plug in your top limit, v of t, velocity at time t, and the bottom limit, velocity at time 0, the left-hand side just turns into v of t minus v of 0. That's cool. Over on the right-hand side, if you integrate negative 10, clearly you get negative 10t, which when you plug in your limits from 0 to t, this gives you negative 10t. So you have v of t minus v of 0 equals negative 10t, and if you add the v, or if you can plug it in right now if you want to, what is v of 0? The starting velocity at time 0 is 20, they said. So you can plug that in for v of 0, and you get v of t minus 20 is negative 10t. Adding the 20 over, you get a master equation for your velocity at any time. Your velocity at any time t arbitrary is negative 10t plus 20. The problem specifically asks you to find the velocity at time 3. So all you got to do now, after you've done all the hard stuff, is just plug 3 in for t. And when you do, negative 10 times 3 is negative 30, plus 20 would be negative 10. So the velocity is negative this time. A lot of times in these problems, when you're talking about acceleration, velocity, and position, all those things, most of the time they're up and down problems, throwing up and down in the air. We're going to talk about if it's not later on. If you're in physics, it's going to be boring, but if you haven't been, it might be something you need to know. Usually you're going to think of up and down as a number line, and up is positive, so it just keeps getting more and more positive, 2, 3, 4, 5, 6, 7, all the way up. And down is negative, so going down negative 1, negative 2, negative 3. It's like an axis kind of going down like this. So when numbers have positives associated with them, that means that it's something about going up. So if x is positive 10, you went up 10, and that's your position. If your velocity is positive 30, that means you're going in the positive direction. In this example, your acceleration is negative. That means your acceleration is in the down direction. So negatives are going to correspond to things down, whether it's position, velocity, or acceleration. And positives are going to indicate something that is going up right there. So there's your answer for number 2. Number 3 is asking you to find the work done. Now this is kind of complicated. In order to move a mass, so they got a mass of 1,000 kilograms, just 1 kilogram, excuse me, a 1 kilogram mass. It's attracted to the earth by gravity, but it takes work to lift it up. And that's true. If you take any object and you try to lift it off the ground, it takes literally work. So this problem is all about how much work is required to do that. Okay, well, here's some basic concepts you need to get down, and I'll talk about them next section specifically. I'll go over them again when we talk about more section 5, 6, which is more about engineering and physics. But for right now, here's what I need you to know. I need you to know what work is, okay? Just accept this. Work is force times a distance. So if I have an object and I push on it with a certain force, and that object moves a certain distance, delta x, by definition, I've done work on it right there, okay? In differential form, if your deltas turn into little d's or something like that, that means that a little bit of change in potential, well, excuse me, down here, a little bit of work, dw, is the force you're applying times a little bit of distance you moved. So you got a force, you moved just a little distance, you did a little bit of work on it. That's the concept of work, okay? How does work relate to potential energy? Well, it's a physics thing again, but long story short, the change in your potential energy, how much energy you gained by doing this, is exactly equal to the negative version of your work. So in differential form, if your triangles go down to d's and stuff like that, then dPe, a little change in potential energy, is equal to a negative dW, a negative value of a little change in work. So essentially, dPe, the change, a little chunk of potential energy change, is just the negative value of a little chunk of work being done, okay? All right, so the problem, let's try to analyze this from the get-go. It says find the change of potential energy when you take this little tiny mass of 1 kilogram and move it 1,000 meters away from the surface of the earth. Well, let's start from the ground up. What is a change in potential energy in general? We just said it. dPe, a little change in potential energy, is negative of a little bit of work done. But what's work done? Well, if you want to hear work is force times a distance. So a little bit of work, dW, is the force you're applying times a little bit of change in position right there. So basically, how we're going to set this up is the change in potential energy is negative of the force involved times dx, or in this case, since you're moving something away from the Earth, kind of radially outwards from it, you could call xr instead, because x represents the radius, how far away you are. A change in position is a change in radius. So in this context, dx and dr would kind of be the same thing. Change in position is the same thing as changing the radius I am away from something. So that's the idea right there. Okay, now what's the force? Well, this is where the physics comes into play even more so. The force between two masses, I don't care how big they are, is going to be given by that equation at the top of the screen, which says negative gm1 m2 over r squared. R represents the distance between their centers. M1 and M2 represent the two masses that are involved. And that big G thing is just some number you plug in your calculator. It's 6.674 times 10 to the negative 11th. It's just a constant, okay? It'd be given to you. But the point is, what are the two masses involved? Well, one of them is the whole Earth, and the other one is just the 1 kilogram object. So what are you going to plug into that top equation way at the top of the screen for M1 and M2? The mass of the Earth and the mass of the object. So one of the masses is the mass of the Earth, which is given to you, 5.97 times 10 to the 24. The other mass is 1. So if you plug those two numbers in for M1 and M2, excuse me, sorry, times that big G, which I just said was some other constant, 6.674 times 10 minus 11. It's a universal gravitational constant. Now divided by their distance squared. Now there's the rub, okay? The distance between them, their centers, is going to change because you're literally moving one away from the other. So it's a variable. It is going to change. I can't plug things in right now because in calc, you don't want to plug in things that change until after you've done all your calculus, because calculus is about change. Okay, but if you simplified the numerator, this negative gm1 m2 thing, you would have got this number out on top of this work, which is negative 3.98438 times 10 minus 14. So the change in my potential energy is negative f dx. So the little change in potential is negative. Here's the f, okay, right here, going to that equation. It's all in terms of r, so I'm not going to say dx, I'm going to say dr, because that's what the change in position represents, a change in radius right there. But it's still a change in position. A change in position, I don't care if I call it x or r or whatever, it's the same concept. So here's the setup, okay, and you clean it all up. Maybe there's a couple of negatives you can put together. But a little change in potential energy as I lift this up is going to be equal to 3.98438 times 10 to the 14th over r squared dr. Like every section in this chapter, that's the hard part, setting up what a little chunk of what I care about is. Now, we're going to, of course, we want to find the total change in energy as I move from one radius, which is one distance between their centers, to another distance between their centers. We want to change that. So I'm going to integrate it, okay? So you slap an integral on this thing. Now, where's the radius start and where's it end? Well, you start on the surface of the Earth. If you're a very tiny object and you're on the surface of the Earth, what's the distance between your centers? Well, it's essentially the distance from you to the center of the Earth. It's the radius of the Earth, which is given by 6.38 times 10 to the 6 meters. So over on the right side, when you start integrating this with respect to r, that's where r starts. It starts at 6.38 times 10 to the 6th. Where does r end? What's the top limit of this? Well, it's going to be whatever that was. That distance was 6.38 times 10 to the 6th. You moved 1,000 meters up, so plus a 10 to the 3rd, because that's what 10 to the 3rd is, 1,000. So your starting radius is the radius of the Earth, 6.38 times 10 to the 6th. Your ending radius is that same radius, but plus 1,000, so plus 10 to the 3rd right there. Now, again, with definite integrals, I'd like you to try to get in a good habit of being mature about it and plugging in the limits as you go. What does the right side represent? The lower limit start and represented your starting radius, and your ending limit represented your ending radius. This is where I started, this is where I ended, okay? So on the other side, on the left side, when you integrate the potential energy, what should its limits be? Well, it's got to correspond to what's going on the other side. So it's the potential energy at the surface at when R is 6.38 times 10 to the sixth, up to your potential energy at the ending point, which is 6.38 times 10 to the sixth plus the 1,000 plus 10 to the third. The left side is easy to integrate. dPe, the integral, that's just PE. So plug in your limits. Top, PE at the top is the PE at the time when R is 6.38 times 10 to the sixth plus 10 to the third. That is not PE times that, that's PE as a function of that. So your potential energy at this radius minus the potential energy at where you started, which was the potential energy at the surface, is equal to, and if you go do the calc on the right-hand side and integrate that, you get this kind of whole thing, which turns out to be, when you punch it all in your calculator, it turns out to be about 9,787.03. Now, what's a good unit for energy? If you've taken a science class before, it's joules. Okay, so that's what it is, 9,787.03 joules. So that's the change in the potential. That's what they ask you for, the change. Ending potential minus starting potential. That's what this side is over here, the potential energy at the outmost radius minus the potential energy at the inmost radius. And that's apparently equal to, that's the change of the potential. So the change of potential is 9,787.03. If you've taken physics, you should know that the approximation for potential energy is mgh. The mass we moved up is, well, let's see, it's 1, right? G is little g, 9.81. The height is 1,000. And if you take 1 times 9.81 times 1,000, you get 9,810 joules. That is a lie. That's not really how much energy it took to move up there, because that's a linear approximation, the one in physics class. The real change in potential energy is this, 9,787.03 joules. Is it close? Yeah. Is our linear approximation pretty good, even all the way up to 1,000? Yeah. Is it exact? Heck no. You need calculus for any quantity that changes as you change the problem. It's a calc thing, and you have to apply some calculus and a bunch of physics concepts to it. But number 3 is very much kind of down the rabbit hole. We'll go in the next lesson. For this one today, our learning goals are just to begin to apply integrals to various areas of science, just projectile motion today, okay? So what's due? Homework 5.4. The class has officially started this week. Anything up through and including 5.4, I will take to the end of the week. After that, it's officially counted late because we are on not high school time, we're on college time. This is a college course. And you've all logged in and had plenty of time to look at the assignments and start working on them, and most of you have gotten these taken care of already. But if you haven't, you have till the end of the week before I start counting lateness on 5.1, 5.2, 5.3, and 5.4. So if you haven't done squat, you got a lot to do this week. But this new one is section 5.5. It is not due until Wednesday of this week. So you got to get that done too. That's due on a Wednesday. It's pretty straightforward. You got a 2-day turnaround on this particular assignment. And after we get done with that, we're going to hit 5, 6, and have like a whole solid week to work on that because it is rough. I'm not going to lie to you. Some things are easy, some things are rough. This next one's going to be rough, but not this one. So let's get through 5.5 and see what we can do. Okay, so chapter 5, application of the definite integral. Here's your summary of section 1. Here's your section 2 summary, section 3 summary, section 4 summary, and that leads us to today. This is section 5.5, notes. Essentially, it's going to be what's written on this slide right here. And it goes over things we've talked about many, many times before. In general, for any dimension, and there might be times when you're working with X's and Y stuff. But if that happens, you'll look at any dimension separately. What's going on in the X's is completely independent, has nothing to do with what's going on in the Y's. So all these differential forms apply in the X direction, and separately, they apply in the Y direction. No matter what direction you're talking about, X's or Y's, and I'll leave in terms of X's usually, just in general, but you could say Y instead. It doesn't really matter what you call your axis. What's velocity? We went over this. If you have your position, and I'll call it X for right now, it could be Y, it could be S, a lot of different letters they could use for where you are. But if you have your position, and you take the derivative with respect to time, you get velocity. So the first differential you're always going to play with, a lot of them, is going to be v is dx over dt. But of course, you can go down another level. So if you have your velocity and you take the derivative of that, dv over dt, you get acceleration. And you can keep going down as many levels, infinitely many levels if you want. The next one has a name too. If you figured out how quickly your acceleration was changing with time, that name is a jerk. It's like jerking something. Your force isn't nice and steady. Your force is changing, so it's more like a yank or a jerk or something like that. If your force is kind of a yank like that, your acceleration is a yank. So your acceleration is not constant. It's kind of going, is changing too. So we call that a jerk right there. And it's a good name for that. You probably won't need to go down to jerks for the homework or anything like that. If it comes up, that's just what it is. Fair enough. Now, what are you going to need for this kind of stuff? Well, this is all going to be about things shot in the air. So one thing to know is how gravity affects things on the surface of the Earth. No matter what body you're on, there is some acceleration due to gravity, but on Earth, there's a specific number. Little g stands for an acceleration, okay? And it is 9.81 meters per second squared if you're using metric. Okay, so if it's in meters and kilograms and all that kind of good stuff that I prefer, use the number 9.81. Now, I think the book uses just 9.8. You might want to use just 9.8 because your answers will be a little different from those in the back of the book if you use the constant a little differently than they use. Now, if it's close enough to the back of the book, it's off by a few decimal places or something like that, but everything else looks dang solid. And if it's 322.1 and you get 319.9, I mean, that's pretty close. And if you use the wrong constant, that could very well be y. So I wouldn't sweat it if you get too close. But that's what little g is, the acceleration due to gravity in the metric. If they're doing the English system, which a lot of problems in this book do, you probably use this one actually more often than the 9.8. If things are in feet and slugs, yeah, that's right. That's the unit for mass in the English system. Or ergs, and that's the unit for energy in the English system. Weird stuff there. Or pounds, or anything that our country uses because we're stubborn. Although you've never heard anybody use an erg or a slug. Even when we get to energy and masses, we just steal the metric systems things and use them for ourselves because nobody says, oh, what's your mass? Oh, it's 6 slugs. Nobody says that. They say like 6 kilograms. But anyway, if it's in feet, then that's English system, and little g would be 32.2 feet per second squared. Again, I think the book just uses 32. So you might just want to use 32 flat and ignore the 0.2 right there. But in general, these equations over on the right all come from either starting with a constant acceleration, integrating once to get velocity, integrating again to get position. The first two are all what you get when you go do that if your acceleration's constant, okay? The one on the bottom is handy sometimes. You can't derive that with calculus. That's more of a conservation of energy kind of thing. It's more of a physics derivation, but it does hold equally as well. So if you find that bottom one to be useful, go right ahead, okay? All right, so that's what your slide's about. Now, over down there on the right, there's a triangle, and the main thing you're going to want to know is if they're talking about something shot off at an angle, and they might give it in radians because this is a math class, but if they shoot something off at an angle, I don't care about this because this is not this is not just X stuff, and this is not just Y stuff. It's X and Y stuff mixed together. I don't want that. Don't look at everything that's going on in the X direction as one idea, and everything that's going up and down the Y direction as a separate idea, okay? So what you want to do is, if they give you a starting velocity this at a certain angle, like this blue curve right here, the first thing you do is you use trigonometry. You will know the length of this hypotenuse. You will know this angle. You can use sine and cosine to split into something called components, okay? And you can figure out how much velocity is in the X direction, this bottom leg right here, and how much velocity that represents up and down. And then you would use those values in your equations. So if they said starting velocity, if you're doing X equations, you're talking about the velocities, accelerations, positions, and all that stuff along the X direction, what would you use for your starting velocity if this thing was shot up at an angle? For your starting velocity, you would use whatever the leg of this hypotenuse is down at the bottom, whatever V naught cosine of theta is. Oh, but what if you're talking about an equation for position and velocity up and down. Well, then I don't care about this thing at a slant. I just care how much of it's going up and down kind of stuff. So I'd use the other leg of this hypotenuse, the one opposite, that's b naught sine theta, for my starting velocity in the y direction. Okay, so those are the big ideas, and we'll get through this. All right. Introducing some basic physics for you. Okay. Newton's second law of motion states that F equals ma. What's that stand for? F is the total forces acting on something. So if you're pushing here, and you're pushing here, and you're pushing there, if you could add up all these forces and turn them into just one, the net force, the total force applied to some mass, some object. Mass is just a measure of how much stuff is there. If you take a force and you apply it to a mass, it will accelerate. Its velocity will change. And it's given by this equation right here, F equals ma. So if you know forces acting on a mass, you also know its acceleration. Conversely, if you know something's acceleration and its mass, you know the force that is acting on it right there. So that's going to be something that comes up quite a bit, especially when we're talking about this unit, because it's going to be the next section too. Next section doesn't matter too, but this one, when you have a force due to gravity, it has a very specific name. It's called weight. But let's dive in with the F equals ma first, okay? Say you have this diver shooting up in the air. They bounce off, and they are going to come back down, common sense, okay? Now, remember earlier I said we're going to call up things positive and down things negative, okay? The force acting on you throughout this is called your weight. And it's your mass times your acceleration, but a special acceleration. Weight is about the force due to gravity. And we all know that the acceleration is due to gravity. It was given on the last slides. It's called little g. Now, so basically they have F equals ma here, but instead of writing a, they're writing g because this is a specific acceleration due to gravity. Why is there a negative sign out in front? Well, because the force is pulling you down. Earth pulls you down. That's a force downwards in the negative direction. That's why that negative sign is there. So you got to be careful about your signs and all that stuff, okay? All right, so let's see here. Well, acceleration is also, in calculus terms, the second derivative of position, okay? Now, in this case, in this problem, they're not calling this axis y, they're not even calling it x, they're calling it h for height, okay? So your acceleration is the second derivative of your height. If you take your height, which is position, take the derivative once, you get velocity, take the derivative twice, you get acceleration. So your acceleration is the second derivative of your height. If you multiply both of these sides of this equation by m, on this side you get ma, mass times acceleration. On this side, you get mass times the second derivative of h, your position. But if on this side you get ma is equal to something. Force equals ma. So if this side is ma, it's just F. Well, what's F? We figured out due to gravity, it's negative mg. So if you take negative mg and plug it in for ma, because that's what force is, you get this equation here. Negative mg is negative mh double prime of t. And dividing through by the mass on both sides, which you're allowed to do because it's positive, you get that the second derivative of position with respect to time is negative g. All that means is what we already said. It just means that no matter what your mass is, if you apply these equations, the acceleration is a constant. It's negative g, negative 32 if you're using feet per second squared kind of stuff. That's handy. That means your acceleration is not a function of time. It's not something weird. Your acceleration is a constant, negative 32, okay? If you're using metric, you say that your constant is negative 9.8. But that's really good to know that your acceleration, A, in general, is just a constant, negative little g, whatever it happens to be. That's cute. Okay. So if you look at this kind of setup here, let's do a problem involving this. If a diving board is 15 feet above the surface, now let's stop right there, okay? The surface of the water is probably something very important where that is, and they're telling you to start 15 feet above it. Well, let's call the water level 0. So what's your starting position? Well, you started 15 feet up, so your starting position is 15. Remember, up and down, they're calling h in this example. So h of 0, h at time 0, the starting height, starting position, is equal to 15. So that's something I'd set up. H of 0 is 15. Okay, but they're 15 above it, and the diver starts off with an initial velocity of 8 feet per second. That's positive. So which way is the diver going? Is he jumping up or is he jumping down? He is jumping up because up is positive. So they're telling you the initial velocity. They're telling you v of 0, v at time 0 at the beginning is 8. And they ask you, what's the diver's velocity at impact? So they're going to jump up, they're going to fall down, and right when they hit that water, right a split second before they smack into it, how fast are they going is the question, okay? So let's see what we can do with that. Well, we start with our assumption. The second derivative of position, so h double prime, or better known as acceleration, is negative g. The only thing acting on this diver is gravity. There's no air resistance, everything's simple, okay? So they jump off, and the only thing causing them to accelerate downwards is gravity. So their acceleration is the acceleration due to gravity. Negative, because gravity is pulling them down, and little g because, that's the constant. What is little g in this case? Everything's in feet. So you choose the appropriate one, 32, negative 32. Note they're using 32. They're not using 32.2. But if you integrate both sides now, and they're going down the road of not using definite integrals, which is fine. If you like my way, it's a little more mature. If you like their way, it's cool too. But if you integrate both sides, well, if you integrate h double prime, the second derivative, you just get back up to the first derivative. So h prime of t is, if you integrate negative 32 with an indefinite integral, it's negative 32t plus c, okay? Now, let's see what we got. Whenever you put an arbitrary constant in there, you got to figure out what it is. That's what the initial conditions are for. Notice that they said the velocity at time 0 back in the day was 8. They start off going at speed h prime, because h is position, so h prime is velocity. V of 0 is 8, or h prime of 0 is 8. So that means when I plug 0 in for t in this equation, I should get out that h prime is equal, f0 is equal to 8. Well, okay. So plug 0 into this equation for t. The whole right side would just turn to c then. So the constant is h prime of 0, or the velocity at time 0, which is 8. So the constant's 8. So I can rewrite my h prime equation now without the constant, because I know what it is. H prime of t is negative 32t plus 8. So I've taken the starting thing at the top of the slide, h double prime of t, the acceleration. I knew the acceleration was negative g. I did an integral. I plugged in some values, and I figured out a master equation for this thing's velocity now, h prime. Well, now we're probably going to go up one more level. I'm not even worried about the problems asking at this point. I'm just going up levels because you're probably going to have to do that no matter what every single time. So let's go up another level. H prime of t is negative 32t plus 8. Okay. Slap a dt on both sides and integrate. You get, well, what's the integral of h prime? H prime is just the derivative of h. So if the derivative of h is h prime, then the integral of h prime is h. So integrating the left side would just give you h of t, your position as a function of t. They're using h for height, because height represents your position. Doesn't matter, x, h, whatever you want to use. Over on the right, if you integrate negative 32t plus 8, well, you get negative 16t squared plus 8t, and again, plus some arbitrary constant that comes along for it. How do you find the arbitrary constant? Well, again, you use the initial conditions. H of 0, their initial height at time 0 was 15. So when I plug in 0 for t into this equation, I should get that h of 0 equals negative 16 times 0 squared plus 8 times 0 plus c, kind of what they're writing right here. And, well, h of 0 was 15. And all this stuff, when you plug in 0 on the right, is just your constant. So your constant is 15. So you can write out the master equation for this thing's height or its position. H of t, when you rewrite it with a constant plugged in 15, is negative 16t squared plus 8t plus 15. Okay? Well, that's cool. Great. So we've got all our equations. We know what the acceleration is. It's negative 32. We know what our velocity is because we integrated it. We integrated that and figured out what our position is. We know everything about this problem. Now it's time to actually solve the thing. What did they ask us to find? What is this thing's velocity when it hits the water? Now, the first thing to worry about, surprisingly, is not the velocity. when it hits the water, that's a condition about telling you where it is. This thing's position is the position of the water right there. Remember what we called the water level? We called it 0. So I want my height at some time to be equal to 0. If you plug 0 into your position equation, you get 0 is negative 16t squared plus 8t plus 15, which factors, or you can use quadratic formula, and you get out 2 different times when your height is 0. One of them is negative, and you throw that away. It's extraneous. What it represents, though, is if you shot off at time 0 and hit the water right there, what if time it ran backwards? Well, you would be coming back from where you started. At some negative time, you'd also be at that water level. So at some negative time, you're at the water level. You would be going up. There's your initial condition. This is when it really starts, and then goes back down. But of course, you don't care about before they jumped. That's just an abstraction. So if your times are negative, throw them away. You don't need them. The time of 5/4 is what I'm going to be used. Okay, now what good is that? Why did I go do this route first? Well, now I know the time they hit the water. That is what I'm going to plug into my velocity equation. So if you go to your h prime equation, which remember h prime is the derivative of position, that's velocity, and you plug in the time of 5/4 because you know that's what time they hit the water, you'll get the velocity when they hit the water, which is negative 32 feet per second. And what's the negative mean? The negative means that this diver is going down, which makes sense. Downs are negatives, ups are positive. That's the whole concept right there. And they convert to miles per hour for no good reason. Okay, here's another one. It's been reported that Michael Jordan can jump 54 inches into the air, ignoring air resistance. What's the initial velocity required to jump this high? Okay. Well, same deal. Okay, we're going to start from the bottom level up. I'm not going to walk you through every step this time, but the second derivative of the acceleration is negative 32. You go up a couple levels, and you don't know what the constant is because you don't know what their starting velocity is. That's what you're trying to find. Well, I don't know. All I know is that this constant, if you do the math and you plug in times 0 anyway, the constant must be whatever your initial velocity is. So if you rewrite this symbolically, that means h prime of t is whatever that constant was, which is the starting velocity. So we'll just call it v with a little subscript 0, v naught is how I'll say that, minus 32t. And if you integrate that again, so you go up one more level, you get the integral of v naught. Well, v naught's a constant, remember, it's a constant. So the integral of a constant with respect to t is just that constant times t. So it's v naught t. Integral of 32t is 16t squared. So your h at some time is v naught t minus 16t squared. Of course, there would be another constant of constant of integration coming up from there. So technically, I should say h of t is v naught of t minus 16t squared plus a constant. But again, you would apply your initial conditions about h of 0. H of 0 is 0. If you plugged in 0 for all your t's, you get 0 equals 0 minus 0 plus a constant. The constant would end up being 0, which is why they didn't bother to write it right there. They skipped a couple steps there. But put your constants in. If you don't like your constants, use your definite integrals like I've been doing. T goes from 0 to t. The thing I care about goes from that thing I care about at 0 to that thing I care about at time t. Either way will work fine. But you get this maximum equation for this thing, okay? Now, here's a conceptual thing to remember. When they talk about a maximum height, when you're at the very top, if you jump straight up and go straight down, at the very top, you stop for a split second. I'm sure you've seen that if you throw a ball up in the air. At the very top, it looks like it just stops and comes back down. And it's because it does. For a split second, at the very maximum, that thing stops and has no speed or no velocity whatsoever. So how do you solve this? Well, the key is the velocity at the top is 0. So if you plug in 0 for your velocity equation, h prime, and you solve for that time, you get that the time is going to be, well, too bad it's in terms of your initial velocity, but it's v naught over 32. Okay, well, I want to know what the actual maximum height is. Well, if you plug this in to your height equation, h of that time is, and if you go clean it all up, it's v naught t. T was v naught over 32 minus 16t squared. Again, that's v naught over 32, which needs to be squared. If you square it and you go clean it all up a little bit, you get v naught squared minus 30 over 32 minus v naught squared over 64, which is v naught squared over 64. So the height at this time is v naught squared over 64. At whatever the maximum height is, it's equal to your initial velocity squared over 64. Now, let's see what we can do here. Remember, they did give you the maximum height. They said it was 54 inches. What a bunch of jerks, because everything else is in feet. So the first thing you need to do is convert 54 inches over to feet. It turns out to be 4.5 feet, so that's what I want to use, okay? So the height is 4.5 feet. We just said the height, though, at the highest spot is v naught squared over 64. So v naught squared over 64 equals 4.5. And after that is trivial. Move things around, take a square root. And should you use the plus or the minus when you take the square root? Remember, Michael Jordan in this example is jumping up, which is positive, so you want to use the positive version of the square root. It turns out to be about 17 feet per second. I don't know why you'd want to convert to miles per hour, but they did, and there you go. Okay, now like I said, in 2 dimensions, all you got to do is the very first thing is if something's going off at a slant, break it into components. Think of this as a little right triangle, okay? You got an angle, you got a hypotenuse. Figure out what this missing side is, and that's your initial velocity in the x direction. Figure out the length of this side is, which is your initial velocity in the y direction. And then you have 2 separate problems, okay? They're like 2 just independent of each other. They have nothing to do with each other. Whatever your starting velocity is in the x direction, that's what you use for v of 0 in any equations related to things going in the x direction. Separately, whatever your starting velocity was in the y direction, that's what you use for v of 0 in any equations that involve y's up and down. And then you just go do the 2 equations separately. Now the main difference between them is going to be up and down stuff has gravity affecting you. Gravity is pulling you up and down. So that equation will be more complicated than the one for the x's, because is there anything pulling on you or causing you to accelerate horizontally? Nope. There's no forces acting on you. The x equations will actually be pretty darn straightforward. So let's see what we can do here. Now again, here's how you would break them up into components, okay? At any stage, okay? This doesn't have to be the starting velocity. It could be at any moment in time, but you're always going to use probably the starting velocity for all your problems. The starting velocity in the x direction, Vx to start, is your starting velocity, the hypotenuse, times the cosine of the angle in between them. The vertical starting velocity, Vy, is V naught times the sine of y. So that's how you can figure out the starting velocities in the x, the starting velocities in the y, based on some random starting velocity shot off at some angle right there. And then you go use those in your things, and that'll be pretty straightforward. Okay. So here's your problem. An object launched at an angle of theta equals pi over 6. That's in radians. So if you're going to use pi over 6, make sure in your calculator you're set to radians. If for some reason they gave you 30 degrees, go set things in degrees. Or just know what they are. Pi over 6 is 30 degrees. You should know what the cosine of 30 is by now. You should know what the sine of 30 is by now. So you could probably just do that in your head a lot faster, but that's okay. They're shot off at this angle. So something's shot off at a 30-degree angle. That's always compared to the horizontal. So whoop, this little angle I'm making right here with my hands, that is a 30-degree angle. It's shot off with a starting velocity of 98 meters per second. Determine the time of flight and the horizontal range, how far to go in the x direction of this projectile. Okay, well, first thing you do, they gave you something off an angle, split into components. I don't want to know at some angle. I want to know what things are in general. Notice also that they gave you that this was all in the units 98 meters per second. Meters. So I want everything to be in meters. Okay. Now we're going to call this axis the x-axis and this y the y-axis like we would normally. Is there acceleration up and down? Yes, it's due to gravity. So the acceleration, okay, y is position, derive that's velocity in the y direction, derive that's acceleration in the y direction. I'm talking about y's right now. Y double prime, the second derivative, the acceleration in the y direction is negative 9.8. 9.8 due to gravity, and negative because it's down. What's the starting velocity in the y direction? Well, this is where you split into components, okay? So notice that the starting velocity in the y direction is just the y component of starting velocity. Starting velocity was 98, shot off at an angle of pi over 6. Sine would give me the opposite side for that. Sine would give me the up and down part. Or just use the equation. But anyway, you plug it in 98 sine of pi over 6 and you get 49. Okay. What's your starting y position? Not primed or anything like that. Well, start on the ground. So if you're on the ground, what coordinate are you if you're on the x-axis or on the origin or anything like that? Your y-coordinate is 0. So you know all your initial conditions. You know that the second derivative is negative 9.8. You know the first derivative at time 0, the velocity is 49. And you know the starting position at time 0 is 0. So let's get integrating, okay? Here we go. If you integrate y double prime, you get y prime. The integral of negative 9.8 is negative 9.8 t. But you put your initial conditions in too, right? There's some constant. Turns out this constant will always be if you're doing it times 0, the constant will always be what the value of the thing is you're talking about times 0. So if you integrated y double prime to get y prime, now we're talking about y prime, the constant will be whatever y prime was at time 0, which according to this equation up here, y prime at time 0 is 49, okay? Integrate that again. Integrate negative 9.8 t, you get negative 4.9 t squared. If you integrate 49, you get 49t. And the constant on the end is going to be whatever the y thing you're talking about, which is y, is at time 0, which was 0. So there's no need for a constant on the end. So all the equations for everything that's going on up and down. This is all vertical stuff I've talked about. This is just what's going on with this projectile up and down wise as it moves through space. So this is equation for its height, y, at any time right there. So they're asking you when the object hits the ground later on. That means when it hits the ground, the y value up and down is a big fat 0. So if you set that equation equal to 0 and go solve for it, you get that t is either 0 or t is 10. What's t equals 0? Well, remember, you're asking when you set this equal to 0 when it hits the ground. It's at the ground at the start when t is 0. So that's why you get that trivial thing. That's the start. That's the launch. You shoot it off, and the next time it hits the ground apparently is after 10 seconds. So we know what time it hits the ground. It hits it after 10 seconds. But the question was, how far did it go horizontally? What was the horizontal range? It shot off here and it landed there. How far did it go? Well, that's X stuff. Luckily, we know what time it hits the ground, though, so we're going to play with that eventually, but we're going to go through the same kind of derivations again. What's x double prime of t? What's the acceleration of x? None. Like we said before, nothing is going on horizontally to cause this thing to speed up or slow down. In fact, it's going at the same speed horizontally the whole way through the problem. So the second derivative is 0. There is no acceleration. Well, we're going to go through the same kind of thing. What's the starting velocity in the x direction? X prime. Well, if you broke down that triangle originally, it's 98 times the cosine of pi over 6, which they leave exact as 49 square root of 3. All right, so let's integrate that, okay? If x double prime of t is 0, and you integrate it once, well, if you integrate x double prime, you get to x prime, right? But what happens when you integrate 0? Well, whose derivative is 0? Some constant. So x prime of t is some constant. But x prime of 0 was 49 square root of 3. So when you plug in 0 into that equation, your constant must be 49 square root of 3, meaning your starting velocity in the x direction was 49 square root of 3, and it'll always be 49 square root of 3 throughout the problem. So let's see. Well, let's integrate this one more time, okay? If x prime of t is 49 square root of 3, and you integrate both sides, on the left, integrating x prime of t will give you x of t. On the right, integrating it will just give you 49 square root of 3 times t, plus a constant. But again, x at time 0 is 0. We're assuming this thing is shot from the origin, where x is 0 and y is 0. And that means that when you plug in 0 for t, you should get out 0 for x, which means your constant is in fact 0. But again, the constant is always whatever the value of the thing is at 0. So you could have just said the constant 0 because it's 0, 0. But anyway, when you do all that, you get a master equation for x as a function of time. Now, cannon got shot off, and we know what time it hit the graph from all the y stuff up and down. So that time was 10. So all we got to do now is plug in t as 10 into our equation, and we get what x is as a function of t. And since x starts at 0, and ended over here at apparently 490 squared of 3, how far to go? 490 squared of 3, which is about 843. And remember, everything was in meters in this problem, so 849 meters would be my answer. All right, so that's the basics of it. Now, there's a couple problems in there that are about some more funky physics. And one is about the Magnus Force. Okay, and this is a kind of obscure thing, but it's kind of good to know. The Magnus Force produced by a spinning object that has a lack of symmetry in the shape of it, kind of like a baseball. A baseball, when you throw it, it spins, but it's not a symmetric object. You got the laces and things like that, and that's what causes things to break, sliders and things like that to change because of this thing called the Magnus Force right here. So it's due to a lack of symmetry in a spinning object. And it can cause the object to change directions and curve in weird ways, which is weird. So the one example they're going to go over today is called the knuckleball. All right. And baseball players claim that this can dance around unpredictably and something really hard if it's in contact, but that's not the point of this. We're going to see what the point of this is. Okay, so according to some physicists that figured this out, the direction of the Magnus Force depends on the exact orientation of the ball's stitches. Okay, so it's kind of weird. In fact, most balls are almost not perfect. There's no perfect equation for it. It's never a perfect thing, so you never know exactly what this Magnus Force on it. But they came up with a master equation for this thing based on the angle that this thing is spun through. So this has nothing to do with x's and y's and stuff like that. Well, it kind of does. But most importantly, we're talking about as this thing spins through an angle theta. What's the force that acts on it? Well, here it is. By their measurements, they have came up with an approximate equation for the force acting on a ball when it's spun, depending on what angle it's spun through. And it's given by negative 0.1 sine of 4 theta pounds. They're using English system. Okay. Where theta is the angle and radian of the ball's position. So this time position does not represent a line. Position represents an angle. Your position is 0 when you've gone 0 degrees. Your position is 2 pi when you've gone all the way around. It's 4 pi when you spun around. So position in this case is your angular position, angular displacement, if you're in physics and recognize that term. But anyway, this is the force acting on it. Now, what it does is when you throw a ball towards a pitcher, this is going to cause a force to bend it side to side. So when we do talk about positions like x's and things like that, it has nothing to do with how far it is from the pitcher to the catcher. It has to do with how much this thing sways back and forth as it comes towards you. So keep that in mind. But anyway, we got the force. Now, Newton's law, second law, F equals ma. In this particular example, they say the mass of a baseball is about 0.01 slugs. Yes, slugs are the units for mass in the English system, which is kind of dumb. But nonetheless, F equals ma. So if over here on this last slide you have an equation for the force, and you want to get an equation for the acceleration, and F equals ma. If you divide both sides by m, then force over mass is acceleration. So if you take this force and you divide by the mass of the baseball they gave you in this example, which is 0.01, you will get an equation for the acceleration of this baseball back and forth as it comes down to you. So what this says is x double prime of t is equal to negative 10 when you divide by the 0.01 by the force. You get negative 10 sine of 4 theta. Okay, remember, x does not have to do, I know the baseball is moving towards you, but x is not that axis. X is how much this baseball is swaying back and forth. So x is kind of this way, and the ball is being thrown towards you, and the x will be a position for how much it curves from the center, basically. Okay. Now, to make it even more complicated, if the ball is spinning at the rate of omega radians per second, so they're telling you how quickly the velocity of this thing is, but an angular velocity. If position, the derivative of that with respect to time, is velocity, but this time our position is measured in radians. How far around have we got? Well, this omega thing would represent how quickly those radians are changing. If it's a very low omega, you're going at very slow change in angles per time. If your omega is big, it's a big change. So your omega here is kind of like your velocity back in the last thing. But they also tell you that it's spinning at this many radians per second. They just flat out do some work for you. They tell you that means that 4 theta, the thing inside the function I care about, because x double prime is -10 sine of 4 theta, they tell you that 4 theta is given by this equation, 4 omega t plus theta naught. Theta naught is your starting angle. You're probably just going to make that 0, okay? Just like normally you make your starting position 0, you make your starting angle 0 right here. But if you go plug that in for 4 theta in the equation, you get this master equation for x double prime of t. It's -10 times the sine of 4 omega t plus theta naught, which seems really complicated. But you can assume that when you first threw the ball, how much is it wiggled back and forth? None, because you just threw it. You just threw it straight. So x of 0 is 0. How much it has swayed the moment you let it go is none, because you're throwing it dead center, so it has not had time to sway back and forth yet due to the spinning or anything like that. So x of 0 is 0. All right, let's see here. So they say specifically for a spin rate of omega is 2 radians per second, so they're telling you how fast this thing is spinning. You could throw it with a little bit of spin or a lot of spin, but they tell it to you what it is. And they assume the starting angle is 0 because that's kind of arbitrary and doesn't matter. Find an equation for the lateral motion, how much does it move back and forth from the center, and graph it from t is 0 to 0.68. Okay, well, here we go. You clean all that up with omegas 2, and you clean up some more, and finally you get down and cut through all the nonsense. This is what you're x double prime of t is -10 times the sine of 8t. Well, that's your angular acceleration. How quick? No, that's how quickly the that's how quickly the position that this thing is swaying. This is kind of like your x-axis. How quickly that's changing. Well, let's see here. That's just back to what we were talking about before. Okay, that's just something moving along a line, just like something shot in the air. Quickly doesn't move along this line. So x double prime of t is going to represent the acceleration along the line perpendicular to the direction of motion. But we can do the same junk we always do. Let's integrate it. Integrate it once, you get -10/8, okay? You're going to go from 0 to t, okay? And it turns out that x prime of 0 is 0. How quickly it's moving from side to side at that moment is 0, because initially you threw it straight. So it's not moving left or right until the spinning takes action later on. So your starting velocity back and forth is 0. And if you go plug in all your initial conditions for that, it turns out that x prime of t turns out to be about 1.25 times the quantity cosine of 8t minus 1. Well, that gives me my angular velocity, how quickly the angle's changing for time. Go up another level. So x of t, well, I better be careful. This isn't theta prime of t, this is x prime of t. That tells me how quickly it's moving back and forth left and right. But I want to know how far it went left and right. So you integrate one more time from angular velocity, or from the velocity of this thing to the position of it. Integrate x prime, you get x. And integrate a 1.25 times the quantity cosine of 8t minus 1. That integral turns into be a 1/8. And then when you apply your limits, again, from 0 to t, you get sine of 8t minus 0. So the master equation for this thing's position turns out to be, when you crunch all the numbers, 0.15625 sine of 8t minus 1.25 times t. Okay, if you go graph that, this is a graph of how much this thing moved from the center versus time. So you can see when you first throw it, it's going straight. It's 0. X is 0. That means it has not moved back and forth at all like this. And I'll say that this side's negative and this side's positive. Doesn't really matter. So as you throw it, it kind of slowly curves towards more negative. The graph is going down towards more negative. So the position goes down to more negative. Look at the bottom of this hump for this whole thing. What's the smallest x value it gets down to? It gets all the way down to -1. That means, and I believe this was all in what, meters? Wasn't it meters? Oh, nope, it's 32, so it's English. So that -1 means, compared to where I threw it first, this thing is going to sway how far outside from the center? A whole foot. It's going to scoot a whole foot over from the dead center. That's kind of cool. And that's a really complicated example that would not be on a test. There might be like one problem about it in your homework, and it kind of takes care of all the setup for you. Essentially, we're doing the same thing we always did with positions in this way, but with angles. And we still integrate it and do the same thing. I know where you are as an angle in terms of radians. I can take the derivative of that with respect to time, and quickly the angle's changing with time. That's your angular velocity, omega. You take the derivative of that, I can figure out how quickly it's accelerating. Angles per time squared, so radians per second squared kind of thing. So very weird example, and that's kind of all there was to that. So that was tricky. Let's do an example specifically from your homework. I always get questions about this every year, so I decided to do it. And here we go. This is 15, okay, and 15A and B, well, they're all kind of intertwined, all these things, velocities and positions, so you might as well just do everything all at once. But anyway, part A says, show that an object dropped from a height h, feet, okay, feet. So remember, G is going to be negative 32, because feet's 32 and negative for down, but we're just dropping it, okay? This is not a two-dimensional problem. This is just something going up and down, okay? So one dimension will suffice. I'm going to call up and down x, okay? Just to stick with x's. I mean, you could call it y, you could call it h. It doesn't matter what you call it, but I'm going to call up and down x. Up is positive, down is negative. Okay, so you're dropping it from a spot h, and you're letting it go, and show that it will hit the ground at this time, capital T is 1/4 square root of h. And show that it has an impact velocity when it hits the ground, how hard to hit it, at negative 8 square root of h. Okay, well, let's see what we got, okay? One thing at a time. The x is up and down. Your acceleration is negative 32 because gravity pulls things down, and it's 32 because it's gravity, and things are in feet. Check. What about your initial conditions? Well, what is x at time 0? Well, it's your starting height, right? Which I just left as a variable, which was h. So x of 0, x at time 0 is h. Okay, believe it as a variable. At this time later, t, when it hits the ground, what do I know about its position x-wise? Well, it hit the ground. So x at that time, capital T, is 0. What do I know about this thing's velocity at the start? Notice it was dropped. So you're about to drop something. How much velocity has it got right now? None. You let it go, and it has no velocity to start, and it accelerates downwards. So v of 0 is 0. All right, now we're going to go through our normal business. Ready? Acceleration is negative 32. What's acceleration? dv over dt, correct? So dv over dt is negative 32. You multiply by dt. You integrate. I like to go the route where you use a definite integral. If you want to have a plus c and figure out what the constant is instead, that's fine with me. I don't care. For me, I'm going to do it. The right side, you're integrating with respect to t. So the limits should be from your starting t to your ending t. Your starting t was 0. Ending t was some arbitrary time t. So that's the limits over there. On the other side, you need to be integrating dv. So where's that go? It goes from your velocity at that starting time, v0, up to your velocity at that ending time, v of t. All right, pretty straightforward integral. Integral of dv is just v. When you plug in the top and bottom limits into that, you get v of t minus v of 0. On the right side, when you integrate negative 32, you just get negative 32t, which when you plug in your limits from t to 0, just turns into negative 32t. Since v of 0 was 0, since it wasn't moving, had no velocity at time 0, plugging in 0 for that gives you that v of t is just negative 32t. Check. All right. But of course, that's just going up the chain one time. You probably got every problem, you're probably going to need to go up both times. I mean, you're really lucky if they ask you something that just requires you to go up once. So again, if your velocity is negative 32t, well, what's velocity? It's the change in position with time. It's dx over dt in this case. So dx over dt is negative 32t. Multiplying through by dt, slap an integral symbol on this again from 0 to t. Well, again, on the right side, you're integrating from 0 to t. So on the left side, you're integrating dx. So limits would be whatever x is at time 0 up to whatever x is at time t. And then same kind of logic, the integral of that dx would just be x. You plug your top and bottom limits, you get xt minus x of 0. Integrating the right-hand side, negative 32t, you get negative 16t squared. Applying your limits from t to 0, you get negative 16t squared. And you know what x of 0 is. It's your starting position, which was h. So plugging in h for x of 0, you get this master equation for x of t is h minus 16t squared. So I know everything about this problem. I know its acceleration is negative 32. I know its velocity at any moment in time is negative 32t. And I know its position at any moment in time is h. So it does depend on what the starting height was, minus 16t squared. Okay. So back to the problem. Show that an object dropped from that height will hit the ground at a time of t is 1/4 square root of h. Well, okay, they're talking about when it hits the ground. When you hit the ground, the one thing you know is that your position is the position of the ground. So at this time, capital T, we would know that x is 0, right? So plugging in t into our capital T into our equation for x, we get that x at capital T, x at the time it hits the ground, is, when you plug in that, you get h minus 16t squared. But like we just said, h at capital T is 0. So you replace h at capital T with 0. You're trying to solve for time. So if you move things around, 16t squared is h. T squared would be h over 16. And when you take the square root, t is the square root of h over 16, which can be done separately. It's the square root of h on top, square root of 16 on bottom, which is 4. You throw away the negative for the square root because the time should be positive in this case. And lo and behold, what do you get? That capital T is whatever the square root of h is divided by 4. That's what they wanted us to show. 1/4 square root of h. We're done. And for part A, they want us to show that the impact velocity, capital V, they decide to call it, is -8 square root of h. Well, this is actually pretty straightforward because we know what time it hits the ground. It's at square root of h over 4. So plugging that time into the velocity equation, we'll find the velocity at that time. V of capital T is -32 times whatever capital T is, which by our results from the last part is square root of h over 4. 32 divided by 4 reduces to 8, so you finally get to the velocity at that time is -8 square root of h. Remember, why is it negative? Because this thing was dropped, so it's going down, so its velocity being negative makes sense because down is negative, and we're pretty good on that. Part B, show that an object propelled from the ground with an initial velocity of v0 feet per second reaches a maximum height of v0 squared over 64. Again, this is one-dimensional stuff. They're just saying, I shot it up, I came back down. No angles, no nothing. They didn't mention any angles, so you can assume it's just straight up in the air. All right, so shot up with a speed of v0, and we want to know what the maximum height's going to be. So let's see if we can do it for part B. Well, start over again because it's different initial conditions. This was shot up. The last one was dropped from part A. It's just totally different. One had no velocity to start. This one is shot up. They're different positions. So let's just rework it from scratch. Here we go. Again, they're talking about feet. So your acceleration up and down is -32, negative because it's pulling you down. Your starting position, x at time 0, was 0 because you're shot off from the ground. And your velocity at time 0, you don't know, but they called that the variable v subscript 0 v0. Okay, so it's a variable, so we're going to have to live with that. Well, here we go again. We start with the bottom level acceleration. We're going to work our way up. dv over dt, acceleration is -32. Multiply by dt, slap some integrals on it, exact same way as the last one. And you get that v of t minus v of 0 is -32t. V of 0 is called v0, so we're going to plug that in. And then if you move things around, solve for v of t, you get v of t is v0, whatever your starting velocity is, -32t. Well, now you got an equation for the velocity. Let's go up another level. So what is velocity? It's dx over dt. So dx over dt is v0 minus 32t times dt. Slap an integral symbol on it, same kind of thing. Make sure they represent the same things on the same side if you're using a definite integral. And you finally, when you have to plug the limits in, get x of t minus x of 0 is v0 t minus 16t squared. X of 0 is known, though. It's 0. So x of t is just v0 t minus 16t squared. Okay, so again, what did we do? We didn't even look at the problem. We just kind of plugged, we knew what acceleration was, we integrated to get velocity, we integrated that to get position, we plugged in any initial conditions we had as we went, and we have all these maximum equations. And now we're going to use them to solve the problem. So show that an object propelled from the ground with an initial velocity of that reaches a maximum height of v0 squared over 64. They're talking about maximum height. The one thing you should know about when something reaches the maximum height is at the very top, its velocity is 0. So it's tempting to play with a height equation or a position equation because you're talking about that, but no, you want to go to velocity instead. So what you know is the velocity at this time And again, we'll just use capital T for the time in question. Okay, lowercase t for all time, capital T for the one we're talking about. The velocity at this time is 0. You're at the maximum height. Well, what's your velocity equation? It's v of t is v naught minus 32t. Plugging in capital T, we get v of capital T is v naught minus 32 capital T. But v of capital T is 0. So substituting that in, you get 0 is v naught minus 32 times capital T. And if you solve for that time, the time is v naught over 32. So the time it reaches this maximum height before it starts coming back down, how much time does it take to get from the ground up? Well, it's v naught over 32, whatever that happens to be. Now the question is, what is the maximum height? And show that it's v naught squared over 64. Well, now I want to know what the actual position is at that time. So I want to know x of capital T. Plugging capital T into our x equation, you get that x of capital T is v naught of capital T minus 16 capital T squared. And since capital T is v naught over 32, if you plug that in, you get that the x at this time is v naught times v naught over 32 minus 16 times the quantity v naught over 32 squared, which I won't bore you with the details. If you squared it and put like terms together, it would be v naught squared over 64, which is what they want us to show. So the maximum x, the highest x is going to reach, is just going to be v naught squared over 64. And since everything was in feet, this is a position, it's also in feet. So there is your solution for 15a and b. It's a lot of work, but essentially it's just doing some really simple integrals. Remember, acceleration integrate gives you velocity. If you want to use an arbitrary constant, be my guest, plug in your initial conditions, figure out what the initial constant is, or you want to integrate with definite integrals, just make sure both limits make sense in the context of their sides, and then you're done. Repeat. Do it again, go up another level to get position, and then you'll be able to figure out everything from that. Most of your problems are not weird things like spinning balls, but most of them are just pretty straightforward, gravity up and down. And again, if something's shot off at an angle, break it into two components, and then you know your starting velocity in the x direction, you know starting velocity in the y direction, and go do those equations separately. Come up with an equation for all the x's, come up with an equation for all the y's, and their initial velocities are going to be the components that you just broke up using basic trigonometry. So there you go, guys. So 5.4 is due today. In theory, I'll be lenient that I will accept that all the way up to the end of the week, but 5.5 is officially assigned today. The lesson is officially started on April 6th. So class has begun. So normal turnaround on these things. 5.5 is definitely due by Wednesday, the 8th. Now, due dates, it says at 3 o'clock online. I don't care as long as I get in before 11:59 p.m., I will give you credit. So as long as it's turned on the right date, I don't care what the time is. But that's going to be due on Wednesday. So get cracking on that. It's not as bad as it looks. I think you'll be just fine. And if you get stuck, read through the section, and you'll be okay. So good luck, everyone.